Okay. So, we study random networks today. So, what is the let us see how random networks can be formed. Okay. So, I think I told you sometimes earlier, but so you have nodes and edge between a node is connected with probability p. Okay. So, this is the simplest random network which we call as Arthur-Shreni graph. So, this is also named as G and P. Okay. Okay. So, now let us do some calculation. So, I want to ask that what is the probability that a node has degree k? In this random network, what is the probability that a node has degree k? So, take a particular node. Okay. So, tell me what will be the probability it has degree k? Very good, n minus 1 C k. So, it has n minus 1 neighbors. So, out of this it can choose k neighbors and connect it with probability p, and the rest it does not connect. N minus k, sorry. Okay. Rest it does not connect. Okay. Great. I should I write it once more, just no problem. Okay. So, now I want to find out. So, this is p k. I want to find out the average degree. So, average degree is yeah. So, that is k into p k summation over all case, okay, easy, and that is okay, no problem. And this can be shown to be equal to n minus 1 into p. You can understand that you can take out n minus, you can take 1 n minus 1 out, and the rest of the things will follow. Clear? So, that is equal to n p if n is large. Okay. So, now we know the average degree is n p. So, what happens is, think of this, n at limit n tends to infinity, okay. So, is a large graph, n tends to infinity. Okay. But z is the average degree. So, that is finite. Okay. Limit n tends to infinity, z is finite, therefore, p tends to 0. Okay. P represents the probability that given to random nodes, what is the given I take two random nodes and with probability p I wire them. Okay. Clear? So, anyway, for practical purpose what we can say, then if I have a node of, if I have a node of degree 1000 of network of degree 1000 of a network of node 1000 where n is equal to 1000, if I have z is equal to say 5 and if I have n is equal to n 1 is equal to 10,000 and z 1 is equal to 5, then p is much p 1 is less than p. Okay. So, that is why what we have is G n p. Okay. So, another way of representing it would have been G n m perhaps. Okay. We can have things in another way, G n m. G n m is every node has degree m. Yeah. Every node has degree m. We can think of a network where every node has degree m. Okay, that would be a special case of G n p.
I didn't understand this question. How you that is a network with n nodes and you are connecting them with probability p. So now
I am telling there is a special case of G n m where every node, there is a special case of G n p where every node will have exact degree p. I try to say I take this node, take this node, take this node, take this node. I tell that this node will have exact m degree 4, this node will have exact 4 degree, this node will have exact 4 degree, this node will have exact 4 degree. Okay. Means the question which you can ask is that how to form such network. Forming this G n p is very clear. Forming G n p is very clear. You have all the nodes. If you have to write a algo, you have all the nodes, just take each pair and connect it with probability p. Fine. But I am asking you to develop a network where it will be G n m, where every node will have exactly m neighbors. We will come to it. Okay. Okay. Second question is, if n tends to infinity, then p k can be written as a Poisson distribution. When n tends to infinity, here p k is written as a binomial distribution, and when n tends to infinity, a Poisson, a binomial distribution tends to a Poisson distribution. So, you can write e to the power minus z, z to the power k and k factorial, okay, where z is equal to n p. Okay, where z is the average, where z is equal to n p. Clear?
In that case, how did you say z will be finite? You said
Yeah. Yeah, that is my see it can be typically z can also be infinite, but I am very good. I am working on a network where z is finite. This is my assumption. Okay. Hmm? No, it is not a finite random network, it is a infinite random networks with each having finite number of neighbors. You can have infinite random neighbors each having infinite number of neighbors, but for all practical purposes if I take internet, okay, it is a infinite network, practically infinite network, but each having finite number of neighbors. Okay. Any real network fall under this category. Okay. Any real large network fall under this category. Okay. Okay. So, this is the simplest form of random graph. There can be another way of random graph, that is random dot product model. Okay. So, now what happens is every node has u, this node u, node v, every node has some vector. Okay. With every node some vector is associated. Okay. Some vector associated, clear, and whether this would join or not depends upon the vector product v u v f vector product of that node. Okay. Vector whether node u and v will get joined depends upon the vector product, vector dot product of v u into v v. Okay. So, the probability that they will get joined depends upon the dot product of v u into v p. So, this is another model and it has been shown that power loss can be built using this. Okay. Okay. So, now the last one which we say is arbitrary degree distribution. So, what is arbitrary degree distribution? Arbitrary degree distribution means you are just given a distribution that p 0 will be 0.1, p 1 will be 0.5, p 2 will be 0.7. Okay. Oh, sorry, it should be equal to 1. So, say you are given this p 1. So, I do not take 0, let us say p 1, 2, 3. So, probability that nodes have degree 1 is 0.1, probability that nodes have degree 2 is 0.2 and probability that degree 3 is 0.7. Okay. Like in the previous GNM, what is that? P m is equal to 1 while 0 for all cases. Okay. In GNM, we have P m is equal to 1. So, now this may look more deterministic sort of network. Okay. It may look more deterministic sort of network, but think of GNM again. Okay. Think of GNM again. So, there can be many GNMs, like you can connect to any m. So, it is there are many configurations possible. It is not that GNM is a single one. So, what does random exactly means? You have the space of all possible GNMs. Can you pick one randomly from that space? So, idea is this: any random network means that if you are you have a power law, you have a degree distribution, that given that degree distribution, you can form perhaps 1000 different networks. Can you design an algorithm so that you sufficiently randomly pick up one from those 1000? Okay. So, that is what you mean random network. Okay. So, take this GNM. So, for that what we have is called the configuration model. So, what happens in configuration model is like this. Sorry. What happens in configuration model is simply like this. So, in each node, so now from the degree distribution, first from pk's, what you can calculate? N case means from pk's you can calculate how many number of nodes will have degree 1, how many number of nodes will have degree 2, how many number of nodes will have degree 3. Like you are given P 1 is equal to 0.1 and if you are told n is equal to say 10. So, then 1, P 2 is equal to 0.2, then 2 nodes and P 3 0.7 means 7 nodes. Okay. So, this is known, clear. Okay. Now, once this is known, drop those nodes, okay, and then create spikes, form those nodes and create spikes. Spikes means just create spikes. So, here everybody has m is equal to 4, everybody is having 4 spikes. Okay. And then randomly join spikes. So, take a spike from here and spike from here and join spike. Take a spike from here and take a spike from here and join. Take a spike from here and spike from here and join it. Okay. This way go on. Okay. And there will be a situation. What situation can arise? Yeah. Okay. If we think that we are taking 2 from different node, that is we can do sufficiently randomly that pick 2. Okay. No, that is we do not choose that. Once the spikes are exhausted, we can suitably keep it out of the node, keep it out of the node list. Yeah, some spikes means what we can see that everything has finished, but this there is a connection between these two, but ultimately everything has finished and these two are left. At the end what we forget 2, we can take 1, that everything is connected and there is a connection this way, but at the end what is left? A spike here and a spike here. Okay. So, there will be parallel edges. Okay. So, once so what we said that first of all we can if we are doing a total random algorithm, like what is the algorithm? Pick a node if it has a spike and then pick a second node if it has a spike. what we can have? We can have self loop if we have this algorithm. Pick a node if it has a spike, then pick a node if it has a spike, then we can have self loops. Okay. Now, you have an algorithm where you say pick a node if it has a spike, pick a node and not the first node if it has a spike, then you avoid self loops.
Pick a node. And second one is
Pick a second node, not the first, except the first node if it has a spike, then it will avoid avoid self loop, but it will not avoid what? Parallel edges. Okay. If it did not avoid parallel edges. So, then what we can do is that if it is a parallel edge, how can we modify the algorithm? If we have pick up the second node, check whether a node already exists. If not, then put this edge, otherwise pick a new edge, new node. Okay.
This may be something this might happen that at the end of the complete operation we may left with a node which has 2 spikes and there is no other node to.
Yeah. So that is what I am telling. So, with this algo what has happened? You have avoided parallel edges. So, when the things are running, you will not have self loop, you will not have parallel edges, but you may end with some situations. Some situations means number one situation is everything is connected, but there are 2 spikes out here. Everybody, all the spikes have gone, but there are 2 spikes out here. So, then that means you can have self loops, you do not have to connect. Okay. And what is the other situation? Everything is connected and this is already connected, but you have a spike out here and a spike out here. So, if you connect that, you will immediately get parallel edge. Okay. Means this can be of many, you can think that there can be many, all of them are connected, and if you go on to connect, you will have parallel edge. So,
Can there be any hanging edges?
yeah, there can be always some hanging edges left, yeah, but that will be typically 1. If you think that hanging edge, that will be just 1. Okay. Clear? So, configuration model, but there has been huge lot of work on this and it is shown that these errors cannot be eliminated. Okay. If you have a sufficiently random network, these errors cannot be eliminated, but for all practical purposes perhaps this errors will be small, okay, and you can avoid it. Okay. You can ignore it. Yeah, you will not. So, if you have to do some parallel edge, you forget, you do not leave those 2 nodes, leave those 2 spikes.
You started with degree distribution,
Yeah.
but finally the graph you get that is not actually jumping with that degree distribution because to satisfy that degree distribution all spikes should
Yeah.
be.
So, what happens is exactly if you have to have this degree distribution, all the spikes has to get connected, but if I drop this and drop this becomes an approximate of this degree distribution.
Then depends on the probability.
No, it becomes an approximation. So, the question is, yeah, for a sufficiently large, see, there are 2 ways people tackle it. So, once if you see this type of edge is it will be small, self loop at the end, self loop containing will be not much, but what it can happen is that you have one edge, this way you can have large numbers of spikes left within the nodes that are already connected. Okay. So, that can always happen, that you have small clicks around and every click you have some spikes left. Okay. That may not be small. So, what happens is then you can have a backtracking algorithm. You backtrack up till certain point and do it and you see it. So, what is in this configuration model, there is no that sort of correct algorithm exactly solvable algorithm and also not much elegant algorithm. You have the backtracking method and you try to minimize the problem. Okay.
So in practice, we need a result which is it does not have loops and parallelism from this algorithm.
Yeah, means we are assuming that we need a network which does not have loops and parallelisms.
What we can do is have multiple runs of this algorithm and get the good results.
Yeah, so that is what you do. You multiply, you can run it multiple times and get the best result. Okay. So anyway, what I want to drive from an algorithm point of view, it will be approximate of the initial given degree distribution, but sufficiently close.
So once we are choosing two nodes, then we are adding edges. That addition of edges is also with probability p, or is it directly?
No, you are directly adding because you have spikes. So when you are choosing two, you are choosing spikes. So it's nothing to do with that probability. You can add with probability p, that will actually lengthen the process, nothing else. Ultimately, you have to add all those spikes.
But in that case, there should not be any spike left at the end of.
What if you run with probability p?
No, if we are adding directly, we are adding two edges.
Yes, so that's what I told you, that already this edge is there. Now everything has finished, and what is left? A spike here and a spike here. So then what to do? Clear? So this is the configuration model by which you can generate a random graph. Clear? Okay. So now we go to a more interesting point, that when we are saying random network like G n comma p. Okay. So does p has anything to do? Okay. Or we say G z, something like this. Okay. So if I think G n comma p at 1 p, at 1 p there will be many, at a particular p there will be many networks, at a particular p there will be many networks. Okay. Question is, do all these networks have a similar behavior, or some behaviors are common for all these networks? Like if we think of water, okay, at temperature 50, there can be many configurations of the molecules of water. Okay. But everybody has some heat content, like heat content same, heat content similar. So you begin to think in that physical terms, that all these graphs are same or not, okay, or have some similarity within themselves or not. So one very interesting questions which you can ask, or which people ask, is that I have this random graph, I try to join them with probability p. Okay. As p is, when p is very small, when p is very small, what will happen? Sparse means it will still be broken into various components. It will not be a connected network. P small means not connected. Okay. And as you increase p,
But so with increasing n, the average degree will also go on increasing.
yeah, so we take n constant. Okay. We are just, n is constant in this case, and I am just going on increasing p. So p is the parameter here. Okay. I am just going on increasing p. So as p increases, at certain point the network will get connected. At certain p the network will get connected. That is why I was talking of z. Okay. So, that n stays transparent, at certain z or at certain average degree the network will get connected. Okay. So, what happens is, it is seen, we will show it also, it is seen that it does not depend upon which configuration of the network you are taking. It does not depend upon it wholly does not depend upon which configurations of network you are taking. Okay. If you have million networks, almost million variations if you have, almost most of them, almost is again a concept which I cannot define, but most of them will get connected. Okay. So, the question is, what was the first question we wanted to ask? That given a p, does p independent of configuration it is producing give some common properties or not? Okay. And the simplest thing which we can see, when p is very small, the network will be disconnected, and as you increase p, the network will get connected. And what we now want to say, is this p independent of the configuration? What we say, yes, we will show it also, that largely most of the networks at that p will get connected. Okay. At that p will get connected. Okay. Now, connection has another interesting connotation. Connection, we use this term giant component. Okay. With connection we use this term giant component. Okay. I was telling also about that water concept. So, you have this place, water begins to drop. Okay. Initially water droplets. So, initially you have separate droplets. Now, you will see that at certain position it forms, it is not a cluster, it forms a component, means it forms a continuous position, and this is actually a giant component. So, giant component, and then you will see that it entire things get connected. So, isolated small thing, small components. So, first step is all drops, then small component, suddenly one giant component, and then the entire network, entire space. So, drops behave in 4 ways. First is individual drops, small components, one giant component, then entire space. Okay. So, giant component is whose size is of the order of the network. Okay. Giant component is whose size is of the order of the network. So, the question you may have followed me. So, what I was telling, that small components, then one giant component. So, the question immediately comes, why not 2 giant component? Why I am again and again telling one giant component? Okay. So, this is the first question which we will try to tackle. Okay. Clear? Okay. So, now let us think of a network. Okay. So, I take nodes. And let us assume that there are two giant components of size n 1 and n 2. No problem. Okay. So, and total number of nodes in the network is n. Okay. So, in order to two giant component exist, what has to be there? If I throw an edge, that shouldn't fall here, that shouldn't fall here. Okay. If I throw an edge, that shouldn't fall here. Okay. So, no edge between n 1 and n 2. So, that means 1 minus I go okay, 1 minus probability of edge between n 1 and n 2. And so, what is the probability? How many edges can fall between n 1 and n 2? N 1 into n 2, n 1 into n 2, and how many total number of edges can be formed? N C 2, N C 2, total number of possible. You are throwing an edge. So, it can take N C 2 positions, out of which this n 1 into n 2 positions should be avoided. Okay. Clear? And how many nodes do you form altogether? How many edges you form altogether if given in a GNP? How many edges you NC2P? These are the total number or n minus 1 C2P, whatever you want to say. These are the total number of edges you form. So, what is the probability that there is no edge? Will be that all these NC2P edges does not fall within this boundary. All these NC2P edges does not fall within this boundary. Agreed? So, that makes it 1 minus n 1 n 2 n C 2 to the power n C 2 P, because all are independent events and I want that none of them falls. Okay. So, okay. Okay. So, I can write it as 1 minus n 1 n 2 n square by 2, means n into n minus 1, I write n square by 2, n square by 2 into p, and I take limit n square by 2 tends to infinity. Okay. So, what happens? You know, limit n tends to infinity 1 minus x n to the power n s e to the power minus x. Okay. So, I am taking limit of this much. So, this becomes e to the power e to the n1 n2 into p, simple. Okay. Okay. And what we have said, n1 is order n, both n1 and n2 are giant components and whose size is order n. This is clear, both n1 and n2 are giant components and whose size is order n. So, n1 is, then I say okay, lambda 1 and I say lambda 1 and lambda 2. Okay. So, this is e to the power lambda 1 into n, lambda 2 into n into p. Okay. No problem. Clear? Yeah, sorry, there will be a minus. Okay. So, now taking this, I go here. Okay, I hope this would be clear. So, taking this, check it here. What is n p? Z. Okay. So, see e to the, so what we can say, lambda 1 lambda 2 into z is constant, a finite constant. So, this becomes e to the power a constant into n. Okay. Where n tends to infinity, n tends to infinity. So, limit n tends to infinity, e to the power minus k n will be 0. So, then probability that no edge between n 1 and n 2 becomes 0. Yeah, for large, we are always talking of large n. Okay, all our calculations are based upon large n. So, then what is the conclusion? What is the take home? Not possible to have two giant components. Okay. So, through some very simple thing, we see a very interesting, we make a very interesting observation that it is not possible to have two giant components. Okay. The next question which we want to ask is that can we find given a z, when do giant component appear? When do giant component appears? Okay. When does giant component appear? Huh? Z is average degree. Huh? Yeah, we do not vary on p, we take n tends to infinity and okay. Okay, question is clear. So, now let us think that the fraction of nodes not in giant component is u. Okay. Okay. So, when will u be not in giant component? Can you tell in terms of its neighbor? When will u be not in giant component? When its neighbors are not in giant component. Okay. So, u, so when is, if it has k neighbors, what is the probability that its neighbors are not in giant component? if the probability that a node is not in giant component is u, means fraction of node, probability that a node is not in giant component, it is same, that a node is not in GC is u. So, now I ask that if it has k neighbors, what is the probability that all its k neighbors are not in giant component? U to the power k. So, u to the power k gives that if k neighbors all not in GC, then u is equal to, now can you say u is equal to, can you, what is the probability that there will be k neighbors? Pk, very good. So, u is equal to summation of all k's Pk u to the power k. U is probability that a node is not in giant component. Huh?
Which one is small and which one is
No, nothing small, everything is small.
Both U's are same.
Both U's are same. That I told, no, first that what is the probability that I am not in giant component, is the probability that all my k neighbors are not in giant component. It is same as the probability that all my k neighbors are not in giant component. And what is the probability that all my k neighbors is not in giant component? Is u to the power k. We basically has to solve this equation. So, we get a closed form equation to calculate u. Okay. Clear? Okay. Very good. Now, let us say what is Pk is e to the power minus z, z to the power k by k factorial. Okay. So, u is equal to then summation k e to the power minus z, z into u to the power k by k factorial. And what is this? You can take out e to the power minus z. Okay. What is this? Very good. This is e to the power z u, because it is again Taylor's expansion. If I e to the power x, what is the expansion of e to the power x? X okay. Remember? So, this becomes e to the power minus z into e to the power z u, and that gives you e to the power minus z 1 minus u. Pk, this is because it is a orthogonal graph. We told that orthogonal graph can have a Poisson is, if n is sufficiently large, it is following a Poisson distribution. Degree Pk is the degree distribution. No, no, we are talking about Ardha-Shreni till now, and Ardha-Shreni pk is this one. Okay. Any problem? Okay. Can I proceed? Okay. Okay. So, then what is S? If S is the size of the giant component, S is 1 minus u. If S is the size of the giant component, S is 1 minus u. So, similarly, so we can write this as this equation. Huh? No, see u is that the fraction of nodes not in giant component, then S is the fraction of nodes in giant component. Is a fraction, is a fraction of nodes in giant component. Okay, is a fraction of nodes in GC. So, then simply this equation can be written as S is equal to 1 minus e to the power minus z s. Okay. And what we can show that if z is equal to, if z is less than 1, with just simple we can show if z is less than 1, this equation will only produce negative s. Okay. This equation, the solution of equation will produce negative s. Okay. Only if s greater than 1, s is positive. So, immediately you get a phase transition, that less than 1 small components, greater than 1 giant component. So, S is called a order parameter. Okay. And this is how the solution behaves. If you see that it becomes, and this is how the value of S goes. At 1 it emerges. So, what we say, the giant component emerges out of nowhere, because there is no continuity. So, there is a big bang sort of thing. Okay. There was nothing and suddenly a giant component emerges. Okay. And then it goes on increasing and covering the entire network. So, this is 1 means giant component size. Okay. So, it emerges, goes very fast in the initial phase, then slowly it gets the entire order parameter. So, this is again a typical percolation theory which we are using in networks. Okay. So, we will continue this, continue with many other interesting results. Thank you.